Okay, welcome back, everybody. So Kris will continue the lecture on combinatorial geometry and Hodge theory. Please.
Thanks. Can you hear me? Now? Okay, good. Thanks for coming back, and thanks to, where is Oliver, for giving me a break yesterday. So I want to digress back to the case of fans, and then hopefully by the end of today recircle to the theorem we saw last time and a generalization of it. So let's start again to some subset of Rn, which is the support of some rational polyhedral fan. And remember that we saw that these, let's write this, the cohomology. In the fan case, it was noticed before I even pointed it out that this was rather easy to compute from the cellular definition. So this was just going to be our Z module, if we're using Z coefficients, Fp at the origin for q equals 0 and 0 otherwise. Okay, but we also saw these compactly supported and Borel-Moore versions, which if you think about the chain complexes, then they have something in each degree, in each dimension. And it's really non-trivial to compute what those are. So what I want to talk about a bit today is, well, how to compute those in some cases, and also how to compactify this picture and extend this notion of cohomology to compactifications and recover something that some of you may have known already. So I want to just remark, or this is a fact, and this will come back in another form later in the lectures, that if we have our X as being matroidal, so still a fan, so meaning that it's equal to the support of one of these matroid fans, in this special case, we can actually, so we have a theorem that tells us that the Borel-Moore homology, so this is when we take the chain complexes where we look at all the faces of the fan. Okay, this was when we read the chain complex down here, we just had one compact cell, that was the origin. This is why this was boring. But there's a non-trivial statement relating, well, when Q is not equal to D, so D is the dimension, that this is 0. And otherwise, so remember this was homology, but this is sort of the Borel-Moore homology here ends up being a kind of cohomology with a shifted degree. Okay, so this is a proven computation, okay, when we could do it. But I want to view this calculation later as a form of this is what we call tropical Poincare duality. And if you think back to your algebraic topology, Poincare duality for non-compact spaces, you formulate it using, say, well, compactly supported or Borel-Moore. There are different variations of formulating it, but I should put isomorphic here. We'll see that we can describe this isomorphism via a map with a cap product with some fundamental class. Okay. But we're still trying to get a handle on when these cohomology groups say anything at all about the cohomology of an algebraic variety, possibly tropicalizing to X. Okay? And at the same time, trying to generalize this cohomology theory to things that don't come from algebraic geometry, for example, all matroids. This statement works whether you're realizable or not. Yeah?
Do I remember correctly, you said last time that if it's locally matroidal, then I think we have this cohomology?
If it's locally matroidal, it's not this easy. So if it's locally matroidal, you have to actually compute something, and I don't know what the cohomology is. When we're in the setup of the theorem of Wiedenberg and Zarkov, Mikalkin, Zarkov, we at least know what the Betti numbers of this cohomology is if we take Q coefficients, when it's locally matroidal. Okay? But otherwise, there's all kinds of examples where I don't know what the Betti numbers would be, for example, if it's locally matroidal and not representable, and it's something more complicated than a fan. I have no idea. Okay, so that's still in the open case. To be able to answer kind of a correspondence theorem between tropical and usual cohomology, we're going to compactify. So we're going to compactify these fans. Oops, let me call this in a kind of tropical way, and following the guide of tropical compactifications introduced by Tevelov. Okay, so the inspiration here will be starting from algebraic geometry and this compactification theory given to us by Tevelov. So now let's suppose that we have, once again, our algebraic variety, and X is trop of this variety. And we're going to fix the fan sigma, whose support is X. And we want sigma to be unimodular. So this is a rational polyhedral fan. Each cone is generated by some integer vectors. I'm going to ask that the collection of integer vectors can be completed to a Zn basis. Okay, so and support. So there's a choice here, right? There's a choice in this sigma, because I said first lecture that this is only given to us really as a set. What Tevelov suggests for us to do is to take the compactification of this algebraic variety in the toric variety defined by sigma. Okay, so sigma is not complete necessarily. So you would think there's the sigma, the toric variety of this is not a compact variety, but it turns out that if you take the closure, I'm going to use this notation for the toric variety. Okay, that this is now complete. This is closed in here. And moreover, this has a stratification by the torus orbits of C sigma. So there's a correspondence between the toric invariant strata of C sigma and the cones of the fan. And when I intersect one of those strata with the closure x bar, I get a strata of x bar. Okay, and I'm going to write for the open strata, so I'm going to write that this is a disjoint union of x sigma. So for every cone of little sigma of sigma, this is the intersection of x bar with the torus invariant strata corresponding to that cone. Okay? And that's basically Tevelov's tropical compactifications for a subvariety of the torus.
You said sigma does not need to be complete, but then you could take also a final space. And so if it's the torus itself, you take the closure.
But so the key here is, so if we take this to be the torus itself, this is Rn. Fix a fan structure on Rn, it's going to be complete then. And now you compactify. So the trick is when this is actually not all of Rn, and you fix a unimodular fan structure on it, the closure here is going to be complete even if this isn't. That's the nice theory of tropical compactifications.
It's the smallest number of orbits we need to add to make.
Exactly, yeah. Okay. So I kind of mentioned last time that there's this extended tropicalization. And that helps us to find some space x bar, which is a compactification of this x. And the way, yeah.
In the case when x is the whole
Yeah?
then the compactification is the whole toric variety? Or?
Yeah. Then these two would be equal in that case. Yeah. Yeah. But there's a choice. Like this is not fixed. This you get to play around with, and we'll see hopefully that that even though we need to choose this, most of what I'm going to define today is completely independent of it. You have to fix a choice, but if you choose another one, you're still good. Okay.
Sorry, one more thing. And then we take x bar by torus element?
Yeah, I'm not going to worry about this. I mean, the shouldness will come up later, but I'm just going to kind of keep it under. It will be an assumption instead of something I'm trying to satisfy. Okay. Okay, so I mentioned that we have this extended tropicalization where we tropicalize orbit by orbit. So here, these are subvariety of tori, each one of these, and I can tropicalize them, and this whole picture kind of makes sense. Okay? And we can call this the tropical compactification of the tropical variety. And in this case, it's obtained by some sort of extended tropicalization, but we can actually give a completely combinatorial sort of formula for this thing. So even when we're not in the realizable case, this x bar is obtained via the cubical compactification of sigma. So sigma is a union of a bunch of cones. Here's a two-dimensional cone in sigma, and we can compactify each cone up to a cube by first taking the one-point compactification alone of each ray, and then adding a new vertex for the two-dimensional cone, and adding those two faces. So there's a way of making every simplicial cone into a cube, and this can be done very combinatorially, even writing down a collection of cells, which one cell will be a pair of sigma tau. So I'll write labels here in a second. For every pair of faces, tau included in sigma in the fan. Okay, so here I had some cones of the original sigma, sigma, tau 1, tau 2, and then some point v. This one, sorry, I can first, so that was the original sigma. I want to upgrade these to elements or so to pairs. I take everybody that was originally there, and I make it comma v. Okay, and everybody else should be a pair of faces. Here I put tau 1 comma tau 1. So I should put equals here. This is not a strict inequality. Let me finish labeling Oliver. And then here I would have sigma comma tau 2 and sigma comma tau 1. Yeah?
Is this a finer set of divisions that
No, this would be the cell division. This would be like, so this is a space. I haven't given you a cell division. The cell division here depends on a choice of sigma, but so does the compactification. I'm saying this sigma bar is a cell structure on x bar.
But you have another set structure, just where it's setting the funnel.
This one, but these aren't cells. These are kind of sets that are fans, and I have to put a fan structure on them. So this does it. The answer to your question is yes, but it's a little subtle. It's not exactly this.
So for adding cubical compactification, this depends on sigma being modular or at least increasing, no?
Yeah, you can do this, but you won't get a cube always. You'll get something else. Yeah. So we can say now the support of sigma bar is this x bar. Okay, but this is a nice cellular structure on this. Yeah?
So how do you define the phase relations on this sigma bar?
Good. You can see from here that you need inclusion of both pairs.
Okay.
Okay? And another thing we can say is that the dimension of one of these pairs is the codimension of tau and sigma. Right, so the points, the zero-dimensional things, are face with the face. Same thing. All right, so very simple example okay, of this picture. Remember, we started with our line that we then tropicalized to get this. So this was our curly x. This was our usual x. What should we do to compactify? We should add in the torus orbits of the open axes. So we actually had punctures here to begin with. And we plug in also a point at infinity. And here we plug in these 3 points. Okay? Okay.
Sorry, this cubical compactification intuitively you can think of as if the fan comes from a polytope, intersection of a polytope in the normal fan.
Yes. Yes, exactly. But not every fan is projective, so yeah. Thank you. Okay. So we're going to want to do take homology or cohomology of these compactified fans. We like compact spaces in algebraic geometry, especially if we want Hodge theory and pure Hodge structures. So let's extend FP to this sigma bar. And I will eventually switch to using Q coefficients, but to give the Z module definition here. So if you take a face of this sigma bar, it's a pair of faces. And we just do a similar thing. Remember, this was generated by the wedges of the, well, let me use gamma here. This, when I just had sigma, this was generated by the wedge p's of these integral lattices in each tangent space. Now quotient by the tangent space of the little tau. So all of these gammas have to be containing sigma, and here we quotient by, before we take the wedge, we quotient by the tangent space of tau. So for example, at any point like this, I take the tangent space to tau 1 and I quotient by the tangent space of tau 1, I just have a point. So wedge p here is going to be usually trivial except for p equals 0. So this is okay, so some of these will vanish, but that's okay. It's still an extension. And we'll do the same thing as before and define the upper p, f upper p, to be just the dual. Okay, so we can now define the cohomology of these compactified fans using these sheaves fp. And here's a nice result where we can actually compute it and relate this to toric geometry. So this was written down with this definition of tropical cohomology with this sheaf by Omid Amini and Mathieu Picarez. So this was in about 21. But actually, I think this theorem, with a slightly, well, quasi-isomorphic definition of tropical cohomology was already known to Briand in 97. In his paper on the structure of the polytope algebra, he introduced something called Hodge spaces for fans that I don't think got much attention. But so sigma will be rational unimodular. So what's important here, too, is that I don't need this to be the support of, its support to be a tropicalization or anything. This is just any fan. It doesn't have to be pure dimensional. No assumptions. Okay, but there is a toric variety for this thing, no matter what. If we look at the sum of the HPPs of, let me say, I want to write x bar here because I want us to remember that this kind of didn't depend on the fan structure, okay? But we should be wary here that the compactification of x depends on the fan that we chose. If I choose a different fan, I would compactify it to something else. So in a sense, tropical homology never depends on the cellular structure, but this x bar, there should be like a sigma on this bar here. That this is isomorphic to the Chow ring of sigma. So this chow ring of sigma, if you haven't seen this before, I need to be careful here. There is a subtlety. I should put Q coefficients. There is something you can say with Z coefficients, but I don't want to bother with it. So this chow ring has a presentation as a polynomial ring. You take a variable for each ray of the fan, each one-dimensional cone in the fan, and then you quotient by an ideal, which is I'll call the SR for Stanley Reisner ideal, plus J, a linear ideal. Okay, so who has seen this chow ring of a matroid fan or chow ring of a fan before? Who wants the definition of these two ideals? It won't be, some people do, okay. Okay, so aside, this won't be so important for us, but just to let you know that's very concrete, that this ideal is a square Freeman-O'Neill ideal, and it's generated by the non-face relations. So if I have two rays that don't form a cone, I quotient by that. Not making a cone. So in our matroid fan, that would be two flats that are not related by inclusion. And J linear, hope I get this right. What we do is we take, for every linear functional on the dual lattice, okay, we want to sum over all of the rays. So this is a linear, this will be a linear form. I'll evaluate that on the smallest integer direction of the ray times the variable. And take the sum over those, and that should be equal to 0. Okay? So this works for any fan, not just your matroid fans. You've maybe seen the presentation for a matroid fan. This is equivalent, even if it looks a bit different. Okay? So what this is saying, though, is that we have this nice isomorphism between the kind of diagonal part. If I just take the sum of the PPs, okay, this is the chow ring. But I had to compactify, so there was some questions, well, when is the tropical homology equal to the chow ring? This is the answer. Okay? You have to first forget anything off the diagonal, if it's indeed there. All right, and take Q coefficients. There are versions with Z coefficients. So Omid and Mathieu call this, what do they call this? They call this this theorem very fancy, the Hodge isomorphism. So it's called the Hodge isomorphism, maybe not with the Hodge theory of matroid fans or other fans that you think you've seen, but Hodge isomorphism in the context of the Hodge conjecture. So they want to think of this as these should be like the algebraic cycles in some variety. Indeed, they are kind of algebraic subvarieties of a toric variety. But you can also make sense of them as tropical algebraic cycles. And it's saying that in the toric case, everything in the diagonal part, the PP part of this sort of tropical Hodge decomposition, comes from algebraic stuff. And I hope next time I want to talk about the tropical Hodge conjecture in more general scenarios and what it actually means and what we know. Okay. Should also say that this A star sigma, even though it's combinatorial from sigma, this is actually the chow ring of C of sigma. This was, in the complete case, a result of Danilov, and then in the non-complete case is a result of, so it was Danilov that wrote down this presentation. In the non-complete case, it's usually attributed to Briand. There is some thinking to do. Another thing we can say is that, well, this chow ring of a toric variety is also actually isomorphic to the cohomology ring of the toric variety. This is absolutely not true for all algebraic varieties, but in this case, it actually is. Okay? So this is sort of saying that we have a relationship between the PP part of the tropical homology of any compactified fan with the cohomology of a non-complete toric variety.
This is a skew coefficient, right?
Yes, thank you. Yeah, yeah. Clear for this, but not so clear here. Yeah.
Is it easy to say what the Hodge's one is?
Yes, but I won't, let me not do it, otherwise I won't get through it. But anyone who wants to hear can ask me after. Yeah. Yeah.
Question and a comment. So the question is, what is known about the numbers that are off the diagonal?
Okay, good. Yes, excellent. Nothing, as far as I know. So, okay, next to nothing. So, and Brion points this out in his paper. So, let me write, okay. In some cases, we'll know and we'll see that today, that in some cases, when we have this, I'm going to, spoiler alert, tropical Poincare duality, the diagonal, off the diagonal will vanish. And then we have a very nice isomorphism. But in his Hodge spaces for fans, when he introduces them in this structure of the polytope algebra paper, I think he speculates about, now I can't remember his indexing or not, but what the meaning of H21 is. You can also show that, okay, so either the lower or the upper diagonal, I'm too close to the board now and I didn't write it down to remember, all vanish. And that you can see from, rather easily from Brion's description. And what Omid and Mathieu basically do is, I think without maybe knowing about Brion's definition, prove that there's another chain complex, which is essentially his, which computes these. And then it becomes obvious that lower, upper diagonal, it vanishes. Yeah. But otherwise, I don't know what the geometric meaning of these are. Yeah?
I think the Stanley Reasoner ideal in general is not the squares, but that's only if the fan is flat. But if you need to put all the non-pieces, that's different.
Okay. Thanks. Thank you. Any other questions or corrections?
So does it hold for a simplicial fan? Because you take Q coefficients. Can this result be extended to the simplicial case?
Actually, yeah. No, actually, here you're absolutely right. I don't actually need the strong unimodular. This works for simplicial because I've taken Q coefficients. Thank you. Soon I'll need unimodular because I'll want this variety to be non-singular. But for this purely kind of combinatorial connection, right? I have this polynomial presentation. I have some kind of, okay, it's a complicated cohomological thing, but on a combinatorial object, you don't need the unimodular if you work over Q. Anything else? This is good. Yeah?
So in the case of toric variety, do you have HPQ would be different from Q? I mean, the HPQ for P different from Q vanishes or not in general for toric variety?
So if it's complete,
It is complete? Okay.
then you're good. Otherwise, you don't know, but we have many examples where they do vanish, and that's what it's going to be part of the punchline of the talk. Some examples where we can actually use, for PQ here, all of this to recover the cohomology of curly X bar, we're going to need vanishing off the diagonal. We'll see this right now. So we're very interested in those examples, but we don't have a full classification of them. Oh, I could have left the title here, because what I want to describe next is what this Hodge isomorphism lets us do to relate, at least get a map between the tropical cohomology and the cohomology of X, this X bar. Okay, so from now on, everything will be with Q coefficients unless otherwise stated, okay? So let me okay. And let me shorthand, just so I don't have to write this direct sum all of the time. Let me write H upper K trop say of x bar, or anything here, this is going to be the direct sum over p plus q equals k of HPQ x bar. Again, q coefficients. I'll write it here, but now it's a definition of this thing. So we're good. Okay. So what this Hodge isomorphism does is it allows us to define a map that, okay, now this is another reason why I don't, okay. This tau will now be a map, not a face, okay? But we'll decorate it with a star, even though I'll explain why I don't really love the star here. But it allows us to define a map from the total tropical cohomology of this x bar to H upper total of, so here there's again q coefficients. Let me just not write it. Q coefficients here. So. And x bar is built with some fan structure, right? Determines x bar and this x bar via this diagram. Okay. So how do we do this? Well, this is the total for all over sum over all PQs. So I'm writing out a diagram that's going to tell me how to get from A to B. We're going to go via C, D, E, or something like that. So here we first project onto this diagonal part. So here we're forgetting something. As you can see why my remark before, we're going to be interested in the cases where P not equal to Q, that this vanishes. Or that this vanishes. Okay, then we have this Hodge isomorphism, which tells us that this is the same thing as A upper star sigma, or if you like, this is the same thing as A upper star of C of sigma, the toric variety. Then here we have an isomorphism between the cohomology. So if you like, this is still a polynomial thing, and this proof is still combinatorial. Here, now we've got back to geometry. This is a cohomology group of the toric variety. Now remember, this x bar lives inside this toric variety, so we have an inclusion map. And when we take cohomology, we get the I star, the reverse inclusion, the reverse map in the reverse direction, the induced map. Okay. So in the one connection that we saw between tropical cohomology and actual cohomology, that was in the complement of a hyperplane arrangement case, right? And I just stated a theorem. This is isomorphic, A is isomorphic to B. Orlok-Solomon is isomorphic to these F upper P's. Nobody asked me if there's a map or what that connection is. And in that proof that we give, there's no map, really. There's nothing kind of functorial about it. It's like you write down a presentation of the Orlok-Solomon algebra, you have this combinatorial definition of FP, you check they're the same. That's it. Now here we actually have a map. I don't really love this star because it's suggested that it's a pullback map. But it's absolutely not a pullback map. I mean, we did some trickery to define it. Tau is not a continuous map from this to its tropicalization. We can't just pull back, right? We had this crushing of stuff with the log. Yeah?
I was thinking, so in terms of superforms, can I think of it as, I don't know, you have superform and topicalization of
You know what, to be honest, I haven't thought about that. Let's talk after my talk. I don't want to say anything on camera that I'll regret later. Thanks.
Can you say what's first vertical and versus?
This is just the projection. So this is the sum over all P plus Q. I just forget. This is forgetting everything off the diagonal. Okay? So you're kind of saying if there was something off the diagonal, get rid of it, right? So you're kind of seeing there's some weakness in this map. We're not going to learn how to relate what's happening off the diagonal to anything in the variety. It's kind of cheating. But this was the kind of map that worked to help us solve solve in a very strong case, a sense, when we can recover the cohomology of curly x bar from x bar. So here's what I mean by in a strong sense. So we defined what it means to be cohomologically tropical. So we said that curly x is cohomologically tropical with respect to sigma, right? Because this was open and we needed to compactify to get this map. So even this whole setup kind of depends on our chosen compactification, or so it seems. If for every cone of the fan, so not just one condition, but many of them. Oh, this was the board I shouldn't have erased, but it's okay. So remember, we have a strata in the compactification for each cone, both the tropical and the complex thing. So I take the closure of that open strata, and that's this x bar sigma. Oh, there's no trop here. This is this bullet of x bar sigma. So this is the closure of the orbit of torus orbit of sigma intersected with x bar. This map is an isomorphism. Okay. Say it again. Yeah, so remember we defined these x upper sigmas to be the strata of x bar, the open strata. Yeah, so okay. I don't think we use, I think we actually just put the bar in our paper on this to make the LaTeX not so ugly, but that is better notation. So this is a big ask. This is not just asking for every, or asking just for, x bar to have this. This is asking for every phase to have this. There's some kind of inductive self-similarity thing that you're asking about. But this does happen. There are varieties where this happens. And we've seen them, but we haven't seen why this is true. So maybe just as an example before we get a statement to know that, because, what's that? Yeah, there you go. Okay, so Kumars is paying attention. Yeah.
Does the tau stand for the tropicalization method? It's built like along the tropicalization method?
It's not. Tau's, no, okay, but fake, right? So we weren't all in agreement of this notation. So this was our definition with, alphabetical order, Axenis, Edward Axenis, my PhD student, Omid, and Mathieu. Okay, and the example, exactly as Kumars pointed out, is one example at least, if you take our sort of linear subspace. So we have some subvariety of the torus with a compactification to a linear subspace of Pn. And we should be, so there's no fan here, right? Well, what fans, with respect to which is this thing cohomologically tropical? Any unimodular fan. Oh, sorry. Here's where I needed unimodular and I didn't write it. Any sigma unimodular fan with support equal to the tropicalization of L. Okay? So we know one fan who has this property, the sigma M that I defined, the actual honest collection of cones. This is saying you don't have to take that one. You can take any tropical compactification of this thing with a unimodular fan, and it'll still be cohomologically tropical. Okay? So how do we get that just hand wavy before we get into it? Why is this thing true? Well, like, let's look at this map. Where can things go wrong? Here we have an isomorphism. Here we have an isomorphism. Here we have a projection. So the second we get anything off the diagonal, we lose. Here, suppose we didn't have things on the diagonal, then this is already an isomorphism. What we need is an isomorphism here too. So we need to know that we have some subvariety of the torus, that when we compactify with respect to some fan, its cohomology is the same as the cohomology of the ambient space as the toric variety. This is a subvariety of a toric variety. This is a toric variety. Why are these two isomorphic? Yeah?
This is probably, well, part of this question should have probably been answered earlier. But in tropical homology, we have exact sequences of pairs.
We have all kinds of things.
Okay.
Yeah, we have all kinds of tools.
Is this diagram sort of compatible with like the exact sequence for the pair X, X bar?
Okay, we'll see how you can get back to the cohomology of X, hopefully by the end of my talk. So let me postpone it till then. Okay? Because we'll be able to prove a theorem, giving us some conditions, if and only if conditions for this to happen. And we'll see that once you prove the theorem, a corollary is that you actually get a map between the open things. And it's maybe not so much for pairs, but it's kind of like spectral sequencing because we have to do it inductively on each strata. Yeah, thanks. Right, so one thing that happens here is that if you take the compactification of this tropical L for any unimodular fan, these are 0 off the diagonal. This is not obvious, but this actually follows from Poincare duality. Okay. And the other thing that we need to know is that this I star is an isomorphism. And that actually is also true. Okay, so these two things you can just check. So we at least have a class of examples where this thing works and where this is cohomologically tropical. The other thing I should say, this feature of it being the case for any choice of sigma is not an artifact of this example. This is actually true in general. So the upshot, or I don't know, I don't want to put warning because it's an upshot actually. It's a good thing. Being this CT, so satisfying this property, is independent of choice of the sigma. So meaning if it works for one sigma, it's going to work for any sigma prime that is also satisfying this. So it's enough to check it on one. You certainly need sigma to define the system of maps, to have these strata. And if you know about the Deligne spectral sequence, you know that you need to choose a compactification in order to make the spectral sequence run, but in the end what you get doesn't depend on this choice. And that's essentially what's happening here too.
Sigma, you change the compactification.
Yes, you change the compactification, but so this really is a property of just this open thing, but to formulate it, you need the compactification. You need a compactification. Okay. So let's state the theorem. That then generalizes this example. And at least gives us the conditions we need in order to recover cohomology from tropicalizations in this very, very strong sense. So we need to assume that, so let X be let X be shown So this was also a notion introduced by Tevelev, but let us just say that this means that every one of these x sigmas is non-singular. So that's an assumption. Then X is cohomologically tropical if we need both these conditions. So one condition is really combinatorial. I'm going to write them down, and then I'm going to explain what these things mean, because it won't be, the notions have not yet been defined. If its tropicalization is a tropical homology manifold. What this will mean is that kind of each strata, or at each face of a stratification of this, we have some kind of tropical Poincare duality happening. If you think homology manifold means that at each open set you have Poincare duality. So we'll have a notion for this. So this is something combinatorial about X. This doesn't see anything about the of Roman X or usual X. But the second one is an algebraic geometry condition, that X is a wunderschön variety. So this is also something that was named by Edward. This is not just schön, but it's even more beautiful than schön, so it's wunderschön. And this has to do with the mixed Hodge structure. So this is says that for every sigma, we need that the strata X sigma is connected, and has a pure Hodge structure of weight 2k of, sorry, I think I didn't put the, yeah, of weight 2k on the kth cohomology group of this. So if you know about the mixed Hodge structures for these open varieties that we get from Deligne's spectral sequence, then you'll know what this means. If not, I'm going to try, hopefully, to write down the first page of this and explain what this means for those of you who are here. And that basically is why the proof works. So.
You want just only that it is a way to pay, or you want it also to be a Hodge type, right? Is that only by
So that will come out of the recursive structure, I think. Yeah. Thank you. Okay. So this tropical Poincare duality, or this tropical homology manifold, is a feature. Is a feature that gives us that this projection along here ends up being an isomorphism. It's a feature that tells us that HPQ for P not equal to Q is equal to 0. And this Hodge-Tate one is, okay, I mean, it's not just enough for one strata. This was the map for one strata, but the kind of whole collection of them satisfying this ends up giving you that this is an isomorphism. Okay, so as I said in this definition, you need to choose a fan structure in order to formulate these maps, but it's independent of this.
So the definition of shown is also.
So for some compactification given by some sigma. And Shen is also independent of this.
But the fan will pick always in the margin.
Yes, yes, thank you. Yes. Okay, so this tropical homology manifold is a condition on having Poincare duality, or we could also maybe say Verdier duality, on each face. So what does it mean for a space to have? So Y will be some polyhedral space, rational polyhedral space. And having Poincare duality, here say with Q coefficients, you can also formulate it with Z coefficients, is to ask for pure dimension D. Is to ask for an isomorphism between these two, this cohomology and this homology group. Okay? And this isomorphism is supposed to be given by capping with something, and this is a tropical fundamental class. So we only have this fundamental class when this is weighted, so we have a weight function, and it's balanced. And we can write this down really explicitly. So this Y, it's something that lives in the Borel-Moore chains, DD, of the space Y itself. And so remember, this was a cellular chain group with some coefficients in FD. So I take a sum over D dimensional cells. I take the weight of it. And then I take the cell, that's the Q part, this part. And the coefficient in here that I take is the single, the unique generator. This thing ends up being isomorphic to Z. The single generator that is oriented of this tangent space that's oriented coherently with the orientation of sigma. Okay? So this is some well-defined recipe for a chain, and turns out that this chain ends up being a homology class, ends up having boundary equal to 0 if and only if your Y with this weight function is balanced. So this is really the only thing that's tropical, beyond the theorem we saw last time. The only thing that's tropical about tropical homology is that we have the balancing condition in this geometry. You get a fundamental class for this homology theory when you're balanced.
So whether Y being a tropical manifold depends on the way it's charged.
Say it again?
So whether Y being a tropical homology manifold depends on the way it's charged.
Yes. 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 And actually, it falls out of this Wunderschön that the weights here, because remember we got the weights from tropicalizing, that these weights were always equal to 1. This is an artifact of the second condition. It's not visible. Okay. So we ask for I want to use this Poincare duality next time because this is a way of saying for some kind of balanced subcomplexes, I get a homology class from them. Okay. And this will help us with a cycle class map and trying to compare tropical algebraic cycles and tropical cohomology cycles next time. So I think I'm running out of time. I had hoped to connect my iPad to show you the proof. And the proof basically comes down to comparing two long exact sequences. So there's a long exact sequence for the cohomology of X from x bar that looks something like hk of the open thing. And then what we put here is a row of the Deligne weight the first page of the Deligne weight spectral sequence. So it looks something like I won't write everything down, including the indices here. If you know it, you can guess what the indices are. But basically, it's a long exact sequence involving mostly the cohomology of the closed strata. There's a 0 here. And the fact that OK, so this without this term here, this is the beginning page of the Deligne weight spectral sequence. And these maps are Geisen maps. And if you don't know what the Geisen map, it's actually rather easy if you think about it in terms of composing inclusion maps in homology with Poincare duality to take you to cohomology. So we have these maps. And to be wunderschön, or affect of being wunderschön, is that this thing, when we put hk of the open part here, is exact. So this is a long exact sequence. And it's a long exact sequence every time, even if I decorate up here with a sigma, and I take the strata, closed strata of sigma, of x sigma. Okay? And so this is from Wunderschön. And being a tropical homology manifold, or in any case, just having tropical Poincare duality on just x itself, gives us, if I replace all of these with h and then trop on the bottom, and then the corresponding strata of the tropical thing, okay, this also is exact. So this falls out from this definition of Poincare duality. And so all we need to do is then induct. So we, sorry, the arrows go the other way. We have these tau star arrows at each step. We don't have it here yet, maybe, let's say. But we have it on all the lower strata. We build it up by induction. And as long as dimension is large enough, we just get it straight up from commutative algebra, we would get an isomorphism here. When it's not long enough, and that's actually when you're in the surface case, you need to do a little bit of work, but we do that work with using an intersection pairing. Okay? But we see if we have all of these being isomorphisms, then at the tail end, which is the open thing, we get this, we even get a map here, and we even get that this is an isomorphism just from the commutative algebra. Okay, so the proof basically goes by induction using both of these two long exact sequences, and the corollary is x is CT also tells us that we have this, oh, there's a trop here, this isomorphism on the open thing. Okay. I think I'll stop here. Let me just also say that I don't have any idea how to classify these Wunderschön varieties, and we know a little bit about how to classify Poincare duality spaces in tropical geometry, but still nothing complete. And if you maybe don't care about tropical cohomology, you might be interested in, well, the Brion's Hodge spaces for fans and toric varieties, right? When is Brion's Hodge spaces for fans actually giving you the cohomology of the toric variety? And this would be an instance of that, when you have tropical Poincare duality. These Wunderschön varieties, so curves, we can classify them. They're P1s minus a bunch of points. It has to be rational. In dimension 2, I don't know if there's like an Enriquez surface with an arrangement of P1s. Each divisor has to be also Wunderschön, right? So meaning that I need to have a rational curve as the components. remove an arrangement of rational curves from an Enrique surface and get something wunderschön? I don't know. I think this could be solved using the intersection form. But if you have any varieties you think might be wunderschön, be happy to take a look at their tropicalizations. Thanks. I'll save the questions for after.